All right, so in this part of the lecture, I'm going to show you how to sketch a Nyquist plot. And so basically, if you remember the previous part of the lecture, I told you that the Nyquist criterion actually it's all based on considering a contour A in the S-plane, where this contour actually encircles the right half plane, just like what you see. So, and of course, this is going to be a this is actually going to be an infinite semicircle. So it really looks like an infinite semicircle. So it's just going to contain the right half plane. So now the question is to find this map, which is really going to be G of j omega, H of j omega. So now what we do is actually to represent the contour associated with this contour A of G, the contour that is actually mapped under G of j omega, H of j omega. So what we do, we're actually looking for a plotting imaginary part of GH in terms of, or versus real part of GH. So in the first example, I'm going to talk about basically how to sketch the Nyquist diagram or the Nyquist plot. So this is actually an example of what is called the speed control system. So the speed control systems have found a wide application throughout industry and also for home application. So this figure that you see, so in the first sub-figure, it really shows one application, and that's actually the output frequency control of electric power from a combination of a turbine and a generator. So here the idea is that by regulating the speed that you actually do here, the control system ensures that the generated frequency is always going to remain within a tolerance, and any deviation from the desired speed are going to be sensed. So now basically, if you think about it, if you just consider this turbine generator, you sense, and then you have a controller. And of course, this sensor is actually going to frequency or a speed measurement. And then you compare it with the desired frequency, and then your controller is actually going to act on it. And then you have a valve, really your actuator is just going to act on a steam, and it's actually going to manipulate the turbine, which is connected to your generator. So you really close the loop using this controller. So now different components of these systems can be modeled using, let's say, if they can somehow model as an LTI system, they can be simply represented as a transfer function. So for a turbine, just going to first order system. For a generator, it's also going to be first order system. And we have an amplifier, valve, actuator, and steam valve. Collectively they can also be modeled as a first order system. And really, if you close the loop, so it's actually going to look like what you see here. So now, and of course, our goal here is not really to design the controller, rather to just analyze, basically using this Nyquist diagram, how to basically sketch the Nyquist plot for a system that has been already designed and in place. And of course, later on, perhaps in the next lecture, I'm going to show you how then you can tune a gain in the feedback path so you can achieve stability if the closed system is not stable. All right, so really this serves just like G. So you actually have the cascade of these three transfer function, and your H, which is this feedback path transfer function, is just going to be unity, 1. Therefore, your G of S, H of S is just going to be the product of these three transfer function, and that is something that is actually shown here. So now to find, of course, G, H at J omega, so we actually need to take this G of S, H of S, and just evaluate that at S equal to J omega. So simply we have to just replace S by J omega. And if we do that, if you just expand this polynomial, it's going to look like this. And if you just replace S by J omega, it's going to be this. And again, remember that here, that's 30, so it's going to remain the same. then we have 43 j omega, which is going to be this, and then here we have 14 j omega square. So j omega square is j square omega square, and remember that j square is just equal to, so j square is just equal to -1. So really we're going to have this 30 and also -14 omega square. So these two combined would actually would be our real part of this imaginary of this complex number. And of course here we also have j cube omega cube, and j cube you can actually break it into j multiplied by j square, and j square is -1, and therefore this whole thing, this j omega cube, is just going to be negative j omega cube, and that's exactly what you see here. And if you just factor j out, so we have j multiplied by 43 omega minus omega cube, which actually comes from this. So now what we have to do in order to sketch the Nyquist plot is actually to figure out how g of j omega, h of j omega behaves around certain frequencies. So 4 frequencies of interest are actually going to be when omega is around 0 radian per second, when omega goes to infinity, and also the frequencies at which either the real part of gh is equal to 0 or the imaginary part of gh is equal to 0. And I'm actually going to show you that in order to handle the first two cases, when omega goes to 0 or goes to infinity, you really should be very careful. And there are actually some details I'm going to explain to you how those details work and how you can effectively utilize some of these math that I'm going to explain to you. All right, so again, this is the same transfer function, g of j omega, h of j omega. So now you see a complex number in the denominator. So in order to convert this to a pure complex number in the form of a plus jb, instead of having a complex number in the denominator, if you want to convert this to a complex number in the numerator, well, like I said, in the form of a plus jb, what you do, you actually multiply both numerator and the denominator of this complex number by the complex conjugate of the denominator. So if you recall, I'm just going to briefly show you how that works. For example, if you have 1 over a plus jb, then you can just multiply this by the complex conjugate of the denominator, which is going to be a minus jb divided by a minus jb, and the result is just going to be a minus jb divided by a squared plus b squared. So now you have a complex number which is in the form of, let's say, c plus jd. So now you can just consider this guy to be your c and this guy to be just your d. So this really would be just c plus jd. Anyway, so now if you just take the same precision and just use it here, so we're actually going to end up with something like this, 500 multiplied by this. So now what you see in the numerator is simply the complex conjugate of the denominator, and of course in the denominator is just going to be this term square plus this term square, and that's exactly what you see. So now let's just see what happens around omega equal to 0, infinity, when the real part is 0, when the imaginary part is 0. So now let's start with what happens at omega equal to 0. So at omega equal to 0, we're going to have 500 multiplied by 30 minus j0 divided by 30 squared plus 0 squared. So the result is just going to be 50 over 3. So that means that when you're going to start drawing your plot, your first point that you're actually going to start drawing, which is associated with omega equal to 0, is just going to be 50 over 3. And of course, it's just going to be a pure real number. I'm actually going to show you how to just connect these different dots and how to actually come up with a meaningful sketch that we're further going to use for other purposes. So now, of course, you're going to also evaluate when the real part is 0 and also when the imaginary part is 0. So now, when the real part is 0, it means that this guy will have to be 0, right? Because denominator is just pure real number, so you just have to see what happens in the numerator. So if the real part of GH is 0, then it means that just this real part will have to be 0, which means negative 14 omega squared plus 30 is equal to 0, and omega would be 1.46 radian per second. So now, if you take this frequency and put it back, so if you just put it back here, so if you just put it back here, this equation, then you are going to end up with GH, which is going to be now negative J8.36. What does that mean? That means that, I mean, initially when omega is equal to 0, you're actually at 15 over 3, which is like 16 point whatever 66, and that's actually a pure real number. So let me just erase this guy right here. So but now, as we increase the frequency at omega equal to 1.46, it's actually going to hit the imaginary axis. At what point? At negative J8.36. So, so if you really want to connect the couple of pieces that we have so far identified, so it's going to, so you actually start, so this point that you see here, that point is really associated with omega equal to 0, and this point is actually 50 over 3. So you start from this this point and you move to negative J 8.36, and this actually happens at what frequency? At frequency of 1.40, I think that was 1.46. Yes. So now, and of course this would be the direction. So now we have so far been able to identify that we start from here and we actually hit the imaginary axis at this point. And of course we're just going to move further, but I'm actually going to show you how we're going to move further. So now to continue, we're also interested in knowing where the imaginary part of GH, or that mapping, is going to be equal to 0. And that is actually going to happen, so that happens when the imaginary part is 0, so we have 43 omega minus omega cube will have to be equal to 0. And if you solve this, then you're going to end up with omega squared equal to 43, or omega equal to square root of 43, which is 6.56. And at this frequency, it turns out that the value of GH is going to be negative 0.874. What does that mean? If I come here, so if I just, because remember, we're increasing omega. So now, here it was omega equal to 0, then here it was omega equal to 1.46, and when it crosses the real axis, it's actually going to be associated with omega equal to 6.56. And when that crosses the real axis, it's just going to cross that real axis at negative 0.874, and that's what you see here. So now, so just to continue the plot, so it's actually going to look like this. And this point here is negative 0.874. And of course, this happens at what frequency? At frequency of omega equal to 6.56 radian per second. Okay. So now we move from omega equal to 0 to here, then to here. And of course, I'm just going to continue on showing you what happens with the rest of it. Okay. So far we have actually covered 3 things: omega equal to 0, when the real part is 0, when the imaginary part is 0. So the next thing I'm going to talk about is what happens around omega equal to infinity. And again, remember that not always you're going to have really well-behaved problems like this, where there is going to be one solution for the imaginary part being equal to 0, one solution for omega equal to 0, what happens around omega equal to 0, and one solution as we saw here for when the imaginary part of GH is equal to 0. And again, you're not necessarily going to have always solution for each of these, but if you do, then that's how you're actually going to approach them. All right. So now for around omega equal to infinity, quite often we actually need to look at the vector representation, because that's going to be the best and most effective solution to address the case of an infinite omega. So now if you remember, in this example, since it was just this 500 divided by s plus 1, so we just had three poles and just the gain of 500 in the numerator. So just like what I discussed in the first part of this lecture, if we use the vector representation, any point that we consider, the magnitude is just going to be 500 divided by, in this case, v1, v2, v3, and v1 is just the distance between that point of interest to this pole, v2 to this pole, and v3 to this pole. And then for magnitude, it's just going to be for the phase angle, it's just going to be the phase angle of 500, which obviously is 0 degrees, minus this phase angle, minus this phase angle, minus this phase angle. So now what I'm going to do is just to show minus the phase angle of the summation of theta 1 plus theta 3 plus theta 10. And so now what is theta 1? That's going to be this angle. What is theta 3? It's going to be this angle. Theta 1 is actually this angle that you see here. Theta 3 is actually going to be this angle, and theta 10 is going to be this angle. Okay. And of course, for any point of interest, you can use this vector representation. All right. So now, when you consider the case with an infinite frequency, so really you're going to let this C go to infinity. So in that case, really your C is just going to be too far, and you're actually interested in knowing what is V1, what is V2, and what is V3, and so what are going to be these three phase angles. And of course, if C is actually on the j omega axis, but it's just very, very far away from this origin, really all these three phase angles are just going to be negative 90 degrees. Positive 90 degrees. So we're actually going to have theta 1, which is this angle, is just going to be like this, 90 degrees. Theta 3 is also going to be 90 degrees. So theta 10 is also going to be 90 degrees. So really, when we are looking at the point, when omega goes to infinity, it is just like all these points, since these are finite poles, are going to be looked at by this point as if they are just origin. So now, just like your C is just too far, and each of these 3 points, just because they are just too far, you can just imagine these just being origin. So in that case, you're actually going to have 3 angles and all going to be the same, 90 degrees. And also for the magnitude, the V1, V2, and V3 are obviously going to be infinity, because C is just too far away from the real axis. So, and because of that, like I said, V1, V2, and V3, when S goes to infinity, so it's just going to be, and again, remember that when omega goes to positive infinity. So later, I'm also going to show you what happens when omega goes to, let's say, negative infinity. So all the V's will go to infinity, and all the phase angles will actually go to positive 90 degrees, and therefore the phase angle is actually going to be, the GH at S equal to j omega when omega goes to positive infinity is just going to be 0 because of this. So now your magnitude is just going to be 500 divided by infinity, which is going to be 0, and that's what you see here. And the phase angles just going to be negative 90 plus 90 plus 90, which is going to be negative 270 degrees. So now, what does that mean? That means that associated with omega equal to infinity, and of course positive infinity, the point corresponding to that on contour B, which is g of j omega h of j omega, is actually going to be very, very, very close to 0, but that actually makes an angle of 90 degrees with the real axis. So it is going to be something like this, really. So it's just going to be something like this. So I'm sorry. So it's actually going to be a point really right here. But that point will be very, very close to the origin, and the phase angle is actually going to be 90 degrees. And again, this is actually going to be finally I'm going to show you, the final Nyquist plot, but I guess for now you just need to know how I actually got this for when omega goes to positive infinity. And again, what I'm going to do next is just to remind everyone that just like root locus, if you remember the root locus, everything like your plot would be symmetric with respect to the horizontal or real axis. So just like that, the Nyquist plot is also going to be always symmetric with respect to the horizontal real axis. And so now basically whatever you have, however shaped, you actually were able to get it associated with positive frequencies. If you just mirror that with respect to the real axis, so the mirror part is actually going to be associated with negative frequencies. So now, for instance, we saw what happens at A. So this would be just your origin, or your omega equal to 0. We also saw what happens at C. So now, basically we have kind of covered going from omega equal to 0, but 0 positive, to positive infinity. So now let's just see what happens if you travel on this infinite semicircle, on this, like what you see here. So when you do that, any point that you consider on this infinite semicircle, any point you consider is still going to have V1, V2, and V3 going to infinity. But for example, if you just consider a point just too far, for example here, these phase angles, theta 1, theta 3, and theta 10 could be 45 degrees, but they're definitely going to drop from 90 degrees. And when you get close to D, these phase angles, and again remember that this D would actually go to negative infinity. So then these phase angles would be negative 90, negative 90, and negative 90. So for each of these three phase angles, theta 1, theta 3, and theta 10, the angle is really going to drop from 90 degrees, which was associated with C, to negative 90 degree, which is now associated with the point D. So any point, as long as they are on this infinite semicircle, the phase angle here combined is going to be the three of them. It's just going to 270 degrees, but if you come here, it's going to be negative 270 degrees. So now at C, really the phase angle of GH is just going to be 0 minus the sum, which would be negative 270 degrees, and that's actually something that I just showed you a few slides ago. So at D, and of course I've used D prime because D prime is actually the mapped point on contour B associated with the point D that was actually on contour A. So the mapped point now, the phase angle is going to be 0 minus negative 270 degrees, which would be 270 degrees. So now what does that mean? It means that to go from positive infinity to negative infinity, you're actually going to rotate from negative 270 degrees to 270 degrees, which gives you 540 degrees rotation, which is equivalent to 1.5 circles. And so this is actually, so this really shows the final Nyquist plot. So now just completely forget about the one part. So let's just see what happens with one part. Well, yeah, so now let's just see, yeah, so let's just see what happens for positive frequencies, and then the negative frequency is just going to whatever sketch of both of Nyquist plot you got, it's just going to the mirrored version of that with respect to the real axis. So now this point A prime was actually associated with the zero frequency. So in fact, I had already shown you a part of it, right? I had already shown you a part of it here. So really, that's the same thing. And then I'm actually going to show you how to continue drawing this or sketching this. All right. So now I had already covered going from omega equal to 0 to this point, which was omega equal to 1.46, and then to omega equal to 6 point something. That was square root of 43. And then if you keep increasing the omega, let's just say going to positive infinity, it's just going to move away. It's just going to go up. And eventually this point C prime is actually going to be associated with positive infinity. So now, even when your omega is actually 0 negative, so now remember this is 0 positive, right? So you're actually going to see exactly the same mirror image here as well. So now you're actually going to, so now, and again, this is, so now in this case, you're actually going to move here. So this is going to be 0 positive and 0 negative, meaning an infinitesimal value greater than 0 and less than 0, I mean in terms of frequency. And so here, this point C prime was actually associated with omega equal to positive infinity. But to go from positive infinity to negative infinity, I showed you that, well, for positive infinity, the phase angle was negative 270 degrees, which is, so it's going to be somewhere here. For negative infinity, it would be 270 degrees, which is actually going to be this angle. So, but now to go from negative 270 to positive 270, you have to really travel 1.5 circle. That's so, and what that means is that you're actually going to have 1.5 circle traveling around this origin until you reach D prime. Why is this important? Because, well, it's important because you cannot just simply connect this point C prime directly to D prime. So you're actually going to have to travel 1.5 circle around this origin, eventually reaching D prime. And of course, you know, rest of it. So now to go from negative infinity to this frequency, which is actually negative 6.47, I'm sorry, 6.56. 6.56. So now exactly why do I have negative 6.56? The reason why I have that is exactly here. You see, the solution to omega squared equal to 43 is really omega equal to 6.56 and also omega equal to negative 6.56. So I can actually choose both of them. And also here, the real part is going to be 0 at omega equal to positive 1.46 and also omega equal to negative 1.40 so 1.46. And because of that, I'm really going to see a symmetry around this real axis, and eventually the whole plot is actually going to look like this. All right, so in the second example that I'm actually going to not do it now, but I'm going to work in class. So I'm actually going to show you how to sketch the Nyquist plot of a unity feedback with g of s equal to s plus 2 over s squared. So this example is actually slightly different than the one I actually worked before, and the reason for that is that here I have poles or zeros located on the j omega axis. And so the trick here is that whenever you have a pole or zero on j omega axis, what you have to do is that you have to just bypass in your contour A, you have to just bypass those, you know, poles or zeros that are specifically on the j omega axis. So in this case, I have two poles. So if I'm just going to draw the configuration, so I'm actually going to have 2 poles here and 1 0 at -2 here. So now when I'm going to decide on what is my contour A, so it is going to be like this. So you have to bypass the j omega axis poles or zero. So in this case, my contour A is actually going to look like this. And of course, remember that your contour A will always have to move clockwise. Okay, so this is actually going to be an example that I'm going to do in class. So some detail are going to follow during the class.